Section 7.3, number 7 from the WebWork looks like this. Find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. So these two curves about the line x equals -1. So as always, we should try to sketch these. Here's a sketch of these two curves. Y equals x squared is our regular old parabola. X equals y squared is our parabola that opens not upward but to the right. So it looks something like this. They definitely hit at the origin right there. It's not too hard to see that they intersect at x equals 1 or y equals 1 right here. So that's the region right there. And then it's going to be revolved around this line over here at x equals -1. If you really want to practice figuring out how these intersect, you could set these two curves equal to each other, either their y values or their x values. So for instance, if you wanted to solve y equals x squared and set that equal to what this would be, which would be y equals square root of x, these two you would get, well, the only places these two are equal to each other is at x equals 0 and x equals 1. X squared equal to the square root of x. Okay, so that's what the region looks like. Now let's try to sketch this region in a little bit more detail so we can use this cylindrical shell method. So I'll draw a slightly longer region. And I'll draw this shape where they intersect from 0 to 1 like that. And I'm going to draw a mirror image of this about revolved around the line x equals -1. So I'll try to draw another shape that looks something like that over here. And it's this revolved shape like that. Okay, something like that. Now, here, we could use the washer method to figure this one out. But since this is section 7.3, let's practice using the cylindrical shell method. The shell method says the volume is the integral of 2 pi radius times the height, dx or dy. Okay, so I got to figure out which it is, dx or dy. So let me draw one of these cylindrical shells. If I pick some value of x right here, it would look something like this. And I'd have this big cylinder that would look something like that. And it would have this little bit of thickness on both sides. And this little bit of thickness is in the x direction. This is dx. So I'm going to integrate mine with respect to x. A good trick is that if you're using the shell method and you're revolving around a vertical line like the y-axis or x equals -1, then it's dx. If we were revolving around the x-axis or another horizontal line, then it would be dy. This is the opposite of the trick for the disk and washer method. Okay, so here we're going to try to figure out what the height and the radius of this shell are with respect to x. First of all, for this region, x is going from 0 to 1. So I know what those limits of integration are right there because x goes from 0 to 1. Coincidentally, if I was doing y also goes from 0 to 1, but here we're doing it with respect to x. Okay, this distance right here is the height. The height of this cylindrical shell. Now, the height is this distance right here, which that is y equals the square root of x. But it's not all the way to the square root of x. I've got to take off this little bit, minus x squared. So this whole distance is square root of x, and this distance right there is y equals x squared. So that's my height right there. Now, the radius is this distance right here. Now, if it was just this distance, we've already written that distance as x. But it's that distance plus a little more, this distance is 1. So I've got 1 and x together, so the radius is going to be x plus 1. And we've done the hard part of this problem, which is the setup. Now let's do the rest of this problem. So I'm just going to multiply this out and integrate. So the volume is, I'll take that 2 pi out, I'll leave the integral from 0 to 1, and let's see what I've got. X times the square root of x is x to the 3 halves. X times negative x squared is negative x cubed. 1 times the square root of x is the square root of x. And 1 times negative x squared is negative x squared. Oops. And that's what I'm going to be integrating with respect to dx. Okay, this is not a very challenging integral, so let's go ahead and plug this in. This is 2 pi times, well, x to the 3 halves plus 1 is 5 halves. Dividing by 5 halves is the same as multiplying by 2/5 minus 1/4 x to the 4th plus, this is x to the 1/2, so I'd have x to the 3 halves divided by 3 halves or multiplied by 2/3 minus 1/3 x cubed. Here I'm evaluating from 0 to 1. I really like those limits of integration from 0 to 1, make this a lot easier. So if I plug in a 1, let's see, I'll have 2/5 minus 1/4 plus 2/3 minus 1/3. That's what I get if I plug in a 1 for all these values of x. If I plug in a 0, I get 0 minus 0 plus 0 minus 0, so I get a big 0. So now I just need to combine these terms. If I wanted to plug this into a calculator to web work, I could, but these aren't too hard to simplify. Let's see. A common denominator between a 5, a 4, and a 3 would be 60. I would need to multiply this 2 by 12, and I'd get 24 over 60 would be the same as 2/5. I'd multiply this 4 by 15 to get 60, so minus 1 times 15 would be minus 15. Here I have a 2/3 minus a third, so that's just 1/3. 1/3 is the same as 20 over 60. Okay, so 24 minus 15 is 9, plus 20 is 29. So let's see, I've got 2 pi times 29 over 60. Or to finish this one up, 2 times 29 would be 58. So 58 pi over 60 would be that final answer. I guess I could cancel out that 2, and I could go back if I wanted to and make it 29 pi over 30. Either way is fine.